In this video, we discuss a geometric approach to solving linear programming. The basic insight that we need for this type of solutions is that a linear equation a1 x1 plus a2 x2 equals b can be seen as a line in the bidimensional plane x1 x2. The line will separate the bidimensional plane into two regions or half planes, one where a1 x1 plus a2 x2 is going to be smaller than b for all the points in here, and the other one where a1 x1 plus a2 x2 is going to be larger than b for all points in this half plane. The same is true for more than two variables as well, but it becomes more difficult to show this in a nice simple drawing. A linear equation a1 x1 plus a2 x2 plus a3 x3 equals b describes a plane separating into two regions, the three-dimensional plane. And in general, a linear equation with n variables can be seen as a hyperplane of dimension n-1 in the n-dimensional plane. Here is an example. Let's say that we have the following constraints: x1 plus 2x2 is smaller than or equal to 4, and x1, x2 are greater than or equal to 0. So we draw the line described by the equation x1 plus 2x2 equals 4. These lines goes through the points 0, 2 and 4, 0, and so it looks something like this. These lines split the plane into two regions. In one of them, x1 plus 2x2 is greater than 4. In the other, x1 plus 2x2 is smaller than 4. And along the line we have the equality. To find out which region above the line or below the line gives us the inequality x1 plus 2x2 is smaller than or equal to 4, it's enough to pick a point, any point above the line, and calculate the expression x1 plus 2x2. So let's choose, for example, this point here, 2, 2. And in this case, we will have x1 plus 2x2 is 2 plus 2 times 2, and this is equal to 6, which is larger than 4. So this means that the region we are looking for must be under the line. Just to make sure, we can calculate the expression also in some point below the line, for example in the origin, and indeed we will find out that 0 plus 2 times 0 is of course 0, which is smaller than 4. So since we have also the additional constraints x1 and x2 have to be greater than or equal to 0, it means that the area where we are going to look for solutions is really going to be this one just here. So here is what this means. Let's assume that we have several constraints as we had on the previous slide, and we look for each of them what's the region of the plane that satisfies the constraint. And let's assume that we conclude that the region where all constraints are satisfied is inside this polygon. And the question will be where in that region a linear expression of the form ax1 plus bx2 is going to get its minimum and its maximum value. So let's draw a line described by a times x1 plus b times x2 equals, say, 20. And perhaps that line is going to be like this. This line, as we already discussed, splits the plane into two regions, above the line and below the line. In one of them, all points x1, x2 will make the expression ax1 plus bx2 to be greater than 20, and in the other region, all points will make the same expression to be smaller than 20. And let's say that in this case, above the line, we have ax plus a times x1 plus b times x2 is greater than 20. And below the line, of course, we will have that ax1 plus bx2 is smaller than 20. So the line ax1 plus bx2 equals 15 is certainly going to be here and is going to be parallel with the one where the expression is equal to 20. And maybe the line ax1 plus bx2 equals to 10 is going to be this one, parallel with the other ones and still lower. We can continue thinking about the parallel lines coming even lower, and they will have an equation a times x1 plus b times x2 equal to a smaller and smaller constant. So as we approach the area where we look to maximize the expression a times x1 plus b times x2, it becomes clear that the expression is going to be maximum in the first point that such a parallel will touch the feasible area, and that will be, in our case, just here. So this means that the expression is going to be maximized in this corner of the polygon. We can continue our reasoning and we will conclude that the expression ax1 plus bx2 is going to get even smaller values as we go with lower parallels. And in fact, it's going to get its minimal value in this region of feasible points in this particular point here. As a matter of fact, this is a well-known mathematical result, and it can be formulated in its most general form as follows. The points satisfying the constraint of a linear program, which we called on the previous slide the feasible region, form a convex set. Now, if the feasible region is bounded, then the objective function attains both its maximum and its minimum value at extreme points of the feasible region. In case the feasible region is unbounded, the objective function might not have a finite optimum. However, if it does, then it's going to be attained at an extreme point. Here is the example of the carpenter's problem that we discussed in the previous video. So let's see how this looks like from a geometric point of view. The first constraint translates into this line. We can easily see that the area we are interested in is below this line because the expression 20 times x1 plus 30 times x2 evaluates to 0 in the origin, which is smaller than 600. The second constraint translates into this line. We can again easily see that the area we are interested in is below this line because the expression 5 times x1 plus 4 times x2 evaluates to 0 in the origin, which is smaller than 120. So together with the last constraints, we conclude that the feasible area where we look for solutions is this green area. As we discussed, the objective function is going to be minimized and maximized over the green area in the corners of that area. Here are its values in those corners. In point A, at coordinates 4, 2, the objective function is going to be $160. In point B, with coordinates 24, 0, the value is going to be 600. In point C, of coordinates 12 and 15, the value is going to be $750. And in point D at coordinate 0, 23, the value is going to be 690. So the maximum is achieved in point C, and this can be seen geometrically because the objective function is represented by lines such as this dotted red line, or parallels to it. And as the parallels go lower, the value of the objective function is smaller, so it's indeed intuitive that the maximum is achieved in point C. So the answer for the carpenter is that he should make 12 tables and 15 bookshelves for a maximum profit, and the profit is going to be $750 per week. So just to summarize this example, what we learn from the geometric approach is that we can simply identify the area of the plane that satisfies all the constraints and then evaluate the objective function only at the corners of that area. It's of course possible that we may get empty feasible solutions. This is because, for example, the constraints are inconsistent, such as asking that a variable is both smaller than 2 and larger than 4. We may also get infinite or unbounded feasible regions, for example, asking only that x is larger than 40. In such a case, the objective function may sometimes increase to infinity, and so there is no maximum point for it. Or in other words, the problem has no solution.